Uh, Thanks very much, Peter. It's a great pleasure to be back here in Singapore, where the weather is very predictable, hot, humid, and the rain is also predictable. And thanks very much to Meng Chuan and the other organizers for this opportunity to give a talk. So I'm sorry about the long title, Exotic Equivariant Cohomology, but like Peter said, it's something to do with Tduality in a background flux. So I'm mainly going to talk about these two pieces of work with Fei Han in the last few years. And especially this last paper, so I'll focus on it at the end. But since this talk is a kind of review also, so I'll also talk about the early work with Peter Boutnick, Jara Evslin, and okay, so this is a summary of my talk. So I'll start with the review, and then I'll ask a question about the winding and momentum in this early papers of with Peter and Jara. Well, it was slightly missing there. So, and then we'll take a digression into a roundabout way to get to the answer by going through loop space. So this is some work I did with Fei Han, and this sort of some version of equivariant cohomology and loop space, and I'll tell you the motivation for constructing it, and then the solution to the exchange of momentum. It's the exchange of momentum winding on the space-time with a flux, and some generalization of these formulae that I got with Peter and Jara. This is work with Fei Han. So these are sort of like exotic Hori formulae, and it involves some interesting new concepts in math, so some twisted integration along the fiber. Okay, so that's the sort of contents. So let me start off with, it's a very simplistic point of view of, say, type 2 string theory. So you have a background flux, which is a three-form flux, which is closed and integral periods. So in the Ramon fields, you can take to be even or odd on forms on Z, satisfying these equations of motion. So D minus H wedge turns out to be a differential because the square is 0 since H is closed. But it's differential on the even or the graded complex because you lose the Z grading when you do that. So you get twisted cohomology, and a refinement gives you twisted K theory, although I'm not going to talk about twisted K theory in my talk today. I just want to keep it as concrete as possible. So, and the last thing is complex value dilaton and axion. Actually, I won't talk much about this. So, and the other thing is other novelties that typically in string theory, they were concerned with compactifying along a circle on spacetime, but here we allow for some twisted, so compactification on a circle bundle as opposed to just a circle. So it's not a product of the circle and a manifold, but it's a circle bundle. So I'm sure many of you have seen this many times. So we assume that Z spacetime is a circle bundle over another manifold M. And the first Chern class, so this is the circle bundle is determined by its first Chern class, which is denoted C1 of Z, and it's a degree 2 cohomology class with integer coefficients on M. And the H flux H, which I said was a three-form, which is closed and integral periods. So it defines, I forgot to put the bracket, it defines a degree 3 cohomology class on Z with integer coefficients. So this is the starting point. You just have this information. And then you get a T-dual. So this is another circle bundle over M. So the first Chern class of this, this T-dual circle bundle is just a Farber integral of H. So if you think of H as a differential form, then it's integration along the circle. Integration along the circle S1. So it gives a degree 2 class with integral periods, and therefore is the, by pre-quantization, is the Chern class of some principal, a unique principal circle bundle. So I'll denote the dual circle by T hat, just to distinguish it. And then I'll say some buzzwords, but I'll do this explicitly, so you don't really need it. So the Giesing sequence, so circle bundles, so all fiber bundles have a spectral sequence, but this degenerates to a long exact sequence called the Giesing sequence. And it enables us to define the T-dual flux, H hat. But I will write it down explicitly. So H hat is not fixed by this data, since any degree 3 class on M integrates to 0. So you can add it to H hat. So it seems like it's not unique. But then if you impose this condition that if you take H and H hat and the cohomology classes agree on the correspondence space, the correspondence space is a subset of the product space Z and Z hat, such that the projections of the 2 points actually project to the same point in M. So on the correspondence space, if H is equal to H hat in cohomology, then it uniquely specifies the T-dual flux. Okay, so, but I'll actually give you a formula for it. So the slogan we had way back is that Tduality for circle bundles is the exchange of the background flux with the Chern class. So, you know, in other words, the new phenomenon, which was not present when we take a, well, so is that there's a change in topology of spacetime if either the background flux is topologically non-trivial or the Chern class is topologically non-trivial. In either case, you'll get that the T-dual spacetimes are not topologically equivalent. So let me give you an example. So let's start with length space, LP1, which is the quotient of the 3-sphere. So the 3-sphere we think as the unit ball inside C2. And Z mod PZ, so acts on S3 by this. So it's a root of unity, 2 pi I k over P. Acting on Z1, Z2 is Z1, and you act the second factor by the root of unity, the pth root of unity. So LP1 is the total space of a circle bundle over the 2-sphere with Chern class equal to P times the generator of the circle, the second cohomology circle. And it turns out that these kind of length spaces have been classified up to homotopy equivalence, up to homeomorphism, etc. So, but LP1 is never homeomorphic to LQ1 if P is not equal to Q. And then an easy check shows that LP1 and with flux Q times the volume form and LQ1 with flux P times the volume form are T-dual pairs. And Tduality is just the exchange of P and Q in this case. So, so let me just take an illustrative example. So L11 is S3, L01 is the product circle bundle, so S2 cross S1. So we get that the T-dual pairs are, if you take S2 cross S1 with H equals the volume form and S3 with H equals 0, that these are T-dual pairs. And you can see this in this diagram. So you get this donut with flux H equals 1. This is T-dual to this to the sphere with flux equals 0. Okay, so yeah. What momentum is flowing on the S1? No, the circle direction is the one which you scale by R and 1 on R. Yeah.
The circle is the Hoffe.
Yeah, on the other side, it's the Hoffe bundle over S2. Yeah. Right. So it turns out that Tduality gives isomorphisms between H-twisted cohomology of Z and H-hat twisted cohomology of Z hat. And you have corresponding thing for K theory. And actually, I should mention that after we wrote a paper, Gaultier and Cavalcanti came up with the current H-twisted current structures, and they showed that the H-twisted current algebra of Z and the H-hat twisted current algebra of Z hat are also isomorphic. So these are twisted generalizations of a smooth analog of something called the Fourier-Mukai transform. And I think we called it the Hori transform, but actually it is some version of the Fourier-Mukai transform. And this is just a geometric analog of the Fourier transform. And I will also indicate a theorem that shows that this Tduality map is an isometry, and it takes a circle radius, the circle fibers of Z of radius R to 1 on R circle fibers of Z hat. Okay, so it's an isometry that way. So it gives more than topology, although many people tend to call this topological Tduality, but there's a little bit more. There's some geometry also. So this is another salient feature of Tduality. So a little bit more detail. So we choose one forms, connection one forms on the circle bundle Z and A hat on Z hat. So then the rules for transforming the Ramon fields are encoded neatly in this equation. So this is called the twisted Fourier-Mukai transform, and it says T star G, where G is an even form, say for instance, is you multiply it, so you first lift it to the correspondence space, you multiply it by this exponential of A by J hat, and you integrate along the circle fiber, and you get a form on the T-dual space, okay? So, and okay, so, and if you took it, so the other thing is, if you took an even form, then the resulting form is an odd form, and if you took an odd form, the resulting form is an even form. So it's a degree shifting sort of map. Okay, here is the computation. Let me just explain how to get the form, the T-dual flux explicitly. So you take, so let F be the curvature of A, and F hat be the curvature of A hat. And we can assume without loss of generality that the flux, the three form with integral periods is invariant under the circle action, because you can always average, and the average form is in the same cohomology class as the original flux, right? So that, so you can always assume that H is invariant. So the Lie derivative of H is 0. And then you also have another form, because you have this connection A, which is a global one form on Z. And you have the curvature of the connection A hat, which is a global two form on the base, and you just lift it up to Z. So I resisted putting all the pullbacks. So, and if you take the difference of these, you see that it's a basic three form. So omega is a basic three form. That means it's invariant and horizontal. So the contraction with respect to the vertical vector field is 0, and the Lie derivative with respect to the vertical vector field is also 0. So omega actually lives on the base. So then define the T-dual free form to be the curvature of A lifted to the T-dual space, wedge A hat, which is a one form, which is a global one form on the T-dual space. So minus the same omega. So it's easy to check that H hat is invariant and it's also closed, right? So this is a little exercise with Lie derivative and contraction. So also note that if you take the difference of these two, so H hat minus H, it's just D of A wedge A hat. So it says that the cohomology class of H hat and the cohomology class of H are equal. But not only that, we get the exact term explicitly. So this was the condition to guarantee uniqueness of the T-dual flux. So T star actually maps, indeed maps DH closed forms G to DH hat closed forms T star G. And now the twisted cohomology, it's a twisted version of the de Rham cohomology. It says that it's a cohomology of the differential forms on Z with differential D minus H wedge. So that was the sort of like equations of motion, so that differential. And Tduality induces a map on twisted cohomologies. That's what it's saying, and it's degree shifted. So I could, since this is only Z mod 2 graded, I can put a plus or minus 1. It's the same thing. So no, at the moment I'm not talking about self-duality here. So, with the flux, is there self-dual, Peter? I don't know. So I'm not sure. Yeah, it's not implemented, so that's all I can say. It's not implemented here.
But this is also not very dimensions.
Yeah, it's not. Yeah, so this works for general circle bundles. So I don't fix a dimension. So the Riemannian metrics on Z and Z hat, as I said, you take any metric on the M, which is the base, and you take the connection one form and use the connection to define, so you take the symmetric tensor product of these, and you scale it by R squared. And for the T-dual, you take the metric, which is the pullback of the metric on M, and the symmetric tensor product of A hat, and scale by R to the minus 2. And if you do this, then in fact, Tduality is an isometry between these invariant forms, which are even or odd on Z, and the invariant forms on Z hat, which are odd or even. And it induces an isomorphism, a degree shifting isomorphism on twisted cohomology, right? So the point is that you can define twisted cohomology using the smaller invariant complex just because of the averaging procedure. And this is exactly sort of looked nice, but then one of the deficiencies was pointed out to us maybe last year or year before by Maxime. So he said that if you take the invariant forms, it's very hard to see then momentum and winding, right? And the exchange of momentum and winding under Tduality is an important feature of Tduality. And so ideally would like to extend this isometry away from just invariant forms. And indeed, we'll do that in this talk. So let me just point out that if you do it naively, so to the other weight spaces, then you see that the usual Fourier-Mukai transform applied to the higher weight spaces is identically 0. So you don't get anything, right? So you have to sort of, on one side, we will extend it across all forms, and the Tdual side, it'll be the thing which we call exotic differential forms. So to make exotic differential forms look natural, so I'll go through loop space and talk about some earlier work with Fei Han. So in 2015. And so we also modify the Fourier-Mukai transform. So we use, instead of integration along the fiber, we use some twisted integration along the fiber, and so on. So right. So this ends the review part of my talk. Yeah. Yes. Yeah. Right. No, at the moment, yeah, there are various generalizations of Tduality on a circle. So these are circle bundles and other things, so you don't see those phenomenon. When you go to tori, high dimensional thing, then you do see it. But that's another direction which we explored for 10 years stuff, and I'm afraid, yes, we came across various things like this, but I'm not talking about it today. So I'm just talking about circle bundles, and even there's this complexity which is there, which we sort of skipped over in our early work. So any other questions? Yeah.
So some of classical motion of students in the Flux.
Yeah.
It's integral matter.
Yeah.
So after Tdual, very still integral, and then when you pick up integral matter,
it's an interesting question, but I have nothing to say on that. Yeah, I don't know, actually. But for circle bundles, it might be complicated because of the curvature and etc. So I don't know whether it destroys integrability, so I'm not sure. Yeah, maybe there's still some cases where it's... So people have studied, like, they've also put the Einstein condition and studied Tduality, like David Baraglia and Pedram Hekmati. So they study... they put the Einstein Maxwell sort of functional and study it on both sides. So under further conditions, there's Tduality of these things also.
Can you put the H fluxes? Can you have cosmetic geometry?
Yeah, there is such a thing, but we didn't study it. This is only bosonic, yeah, I guess. Yeah. Yeah, so this is the current algebroid picture. So that generalizes the twisted cohomology picture, but it doesn't generalize twisted K-theory isomorphism. So their current algebroid picture is more general when it comes to differential forms. Actually, we have results for that, but I'm not going to talk about it just for simplicity. So they also look at the invariant current algebroid, but I'm saying we also can extend that to exotic versions of these things. So let me now go to loop space, and it seems like a big jump. Why do you want to go to loop space? But there is a reason for doing it, and it'll come to in the last part of my talk. So some motivation for construction. So Tia, who worked out an idea of Witten, revealed a remarkable fact that the index of the Dirac operator on a compact spin manifold it can be formally interpreted as the integral of some equivariantly closed differential form on loop space. And the circle action, the equivariant, is with respect to the rotation action of loops. So you can always rotate the domain of the loop, and that gives you a circle action. But this thing is in some sense formal, although Tia tried to use stochastic integration, etc. But typically it's formal because the integration over infinite dimensional space is not well defined. The problem with the Wiener measure is that it's supported on continuous objects, and it's the smooth ones are measure zero with respect to it. A formal application of localization formula of Deutsch-Zermatt-Heckman leads to the index theorem of a T.S. Singer for Dirac operators. So this was proved by, let's say, Atiyah and Witten. So, and then Bismuth had an important contribution. So he actually allowed the Dirac operator to be twisted by a vector bundle with a connection. So as we know by Atiyah Singer philosophy, that the twisted Dirac operator actually exhausts all the symbols of pseudo-differential operators in K-theory. So if you know how to, if you understand the twisted Dirac operator, the index of twisted Dirac operator, then you know it for all operators, elliptic operators. So in doing so, he constructed an equivariantly closed form on loop space, lifting to loop space the Chern character of a vector bundle with connection. So I'll try and make this more explicit in my next slide. So Bismuth's construction of the loop space refinement of the Chern character form can be viewed roughly as the solution to an equation which is analogous to the holonomy of a connection. So it'll be like a time-ordered integral. So path-ordered exponential, path-ordered exponential. It's a trace of a path-ordered exponential. So Witten sort of suggested that there was, if you look at the cohomology of loop space with respect to the rotation action of loops, then it localizes by just a restriction to the constant loops to an isomorphism of the cohomology of Z with sort of localized. So you have Z, Z inverse. These are variables. Z is of degree 2. And it was formally proved by Jones and Petrak a few years later. So just to say, so you take the cohomology of, equivariant cohomology of loop space, and you localize it. So, and you take the restriction to the constant loops, and you get this isomorphism. So there's a way to lift things to loop space. And so in some sense, the space-time is a shadow of what happens on loop space. Right? So, and also Bismuth, so there's a Chern character from the KT of spacetime to cohomology of spacetime, and I put U inverse, but you could put the Chern character. You can so the Chern character, as you saw in of say E and Nabla, is a trace of E to the curvature, right? But now you can put a U here. So U has degree 2, and this is a 2 form. So it has total degree 0, right? So, and this is this Chern character map, which encodes this. And then he lifted it. This is Bismuth, lifted it to an explicit equivariantly closed form, which is BCH, Bismuth Chern character. And then you have this localization map, and this diagram actually commutes. So our goal was to try and do this for twisted cohomology. So we wanted to find the cohomology theory on loop space, which localized to twisted cohomology. You might think this is rather straightforward, but the answer might surprise you because it surprised us also. This twisted cohomology was first studied by Rome Witten, and it sort of is the charge group for d-brane charges in flux, at least rationally. So there also, I just want to mention that there are applications to math, such as the twisted ether, twisted analytic torsion, and so on. So some of this, yeah.
Can you tell me what the operator is that the equivariant
in this case, it's just equivariant differential. So you have differential forms on loop space, yeah, and they are invariant forms. So invariant under the rotation action, and the differential is the Cartan differential. So d minus I k. K is the rotation vector field. And so it's this. So if you square this, you get the Lie derivative, and that vanishes on invariant forms. Okay, so it's just so you can jazz this up to so this increases degree by 1, this decreases degree by 1. So to fix this, you can multiply by u also, right? And over here, you put in u. You know. So then you get an actual, the Z grading is fixed. But these are all, yeah, fine information, but it's just equivariant cohomology of loop space. So it turns out that it's this exotic equivariant cohomology on loop space that localizes to twisted cohomology. So what's, let me just tell you some features, and then I'll explain this cohomology theory well. But some features are that it's differential forms on loop space, right? But it's not any more scale valued there, but it's valued in some line bundle. So this line bundle, it turns out to be non-flat. So typically when you talk about cohomology, you take flat vector bundles, right? So here is an interesting thing that actually L is not flat. And then you take the invariant part here, and then the differential is a little bit more complicated, and it involves, so the fact that L is not just arbitrary line bundle, but it's a line bundle associated with the three-form flux. So I'm going to explain all this. So this three-form flux corresponds to a gerb, and this line bundle is the holonomy of that gerb. So there's a tight relationship between H and the line bundle, and you get a rigid differential, just one differential, which squares to 0. So I hope to tell you this. So there's some connection on this line bundle, and minus IK, just like in the Cartan differential here, and you add some version of H on loop space. So I'll explain these terms, and this differential actually squares to 0 again. So this is remarkable. It took a very long time staring at it to finally come up with it. So just a few minutes before I was leaving for the airport, so we came up with this, Faye and I, sort of. And it still held water when we, so anyway. So I'll try to explain. I think there are various things. So this is not a connection anymore. It's a super connection. It's an equivariantly flat superconnection. So it's, you know, equivalent, and it's kind of the first sort of superconnection I've seen come up just naturally, let's say. It's forced on you. So let me talk about gerbs first. I know there are some students in the audience, so of course these were all mentioned in passing by many people like Hisham and Urs and all, but I'm actually going to define it. So consider a pair ZH where Z is spacetime, and so I'm not saying of any dimension, and H is a background flux, so closed free form on Z with integer periods. Okay, so we want to study, first of all, we want an open cover, not just an arbitrary open cover of the manifold, but also which covers loop space. So we want open covers of Z such that the loops of this open cover is an open cover of loop space of Z. So the problem is that, of course, if you take the usual convex cover of a manifold, this will not satisfy this property, right? So we suppose that you have, consider a maximal open cover, U alpha of Z, with the property that H2 and H3 of this, of all overlaps of this cover, in this cover, is 0. So this is called a Berlinski open cover. Notice that we don't put the condition on H1, and in fact you can't. Because if you take long loops in the manifold, you want the cover of long loops to be also included. So in other words, if you take any loop and you take like a tubular neighborhood of that loop, then that's a kind of Berlinski open cover, for instance. So then the loops on U alpha is also an open cover of loop space. So now, so let H be a closed tree form with integer periods, then H restricted to U alpha is dB alpha, since we are assuming that H3 of these open sets are 0. So B alpha is a 2 form on this open set. And B beta minus B alpha is dA alpha beta, since H2 of this overlap is also 0. Then this triple H, B, and A, so H is a global 3 form, but B is local 2 forms, and A is actually a 1 form on the double overlaps. So this defines a connective structure or connection for gerb. So let's call the gerb GB on Z. So it's not just a gerb, but it's a gerb with connection. So of course, so the goal is to define the holonomy. So, well, let me just say what the gerb actually is. So a gerb is a collection of line bundles, L alpha beta on double overlaps, such that on the triple overlap, U alpha intersect U beta intersect U gamma, there is a trivialization of the triple tensor product, right? So there's an actual trivialization, so I'll call that phi alpha beta gamma. So phi alpha beta gamma, it's easy to see that it's a U1 valued check to cocycle, and that represents the invariant of the gerb. So that's the Dixmeier-Dubé invariant of the gerb. And up to some equivalence, which I don't want to define, the gerbs are classified by these H3 with integer coefficients. And what's a trivial gerb? It's also important to know what a trivial gerb is. A trivial gerb is given by any collection of line bundles, local line bundles. So they don't have to glue up. And you write the gerb as L alpha tensor L beta dual, right, on the double overlaps. So this is gerb, and you can see this picture. So the line bundle is on these overlaps, and on the triple overlap, it's trivialized, the triple tensor product. So here are some examples of gerbs. The first is the spin C gerb. So as we know, at least many of us know that so spin C, there's an obstruction to having a spin C structure on a manifold, and that's given by the third integral Stiefel-Whitney class. But however, so you cannot, but I'm saying every oriented manifold has a spin C gerb. So let's say Z is oriented and it has a Riemannian structure, so you can define the bundle of oriented orthonormal frames, and let G alpha beta be the transition functions of this frame bundle. So also note that SO spin C is a U1 central extension of SON. So spin C, maybe I should write it, yeah. So spin C is just spin cross U1 mod Z2. So Z2 on spin by plus minus the identity, and it acts on U1 by plus minus 1, right? So it's the quotient of spin cross U1. So, sorry, let L be the associated line bundle of this principal circle bundle over SON. So L is just given explicitly by this. Then the pullback under the transition functions of L is exactly the gerb, which is called the spin C gerb. And the Dixmeier-Daudet class of this gerb turns out to be exactly the third integral Stiefel-Whitney class, W3. And so every oriented manifold has a spin C gerb. It also works not just for the tangent bundle, but for any oriented vector bundle. And this is kind of like the universal case. So, let H be an infinite dimensional Hilbert space. And U be the unitary operators on H. Then sort of a well-known but remarkable fact is that U is contractible. So, of course, there are many topologies on bounded operators, but it's contractible in all of them. So in the norm, strong, weak topology, it's contractible. So it's a remarkable fact. So it tells you that the projective unitary group, PU, which is just the unitary group divided by circle multiples of the identity, right? The circle subgroup inside the unitary group. So, of course, it's the contractible space divided by the circle, and therefore it's the classifying space of the circle. It's a model for the classifying space of the circle. So this right. So we have this central extension because projective unitary group is just a quotient. So we have this canonical central extension. It's a non-trivial, and let L be the associated line bundle. Then the gerb is the pullback of a PU bundle of L under the transition functions of a principal PU bundle. So this is kind of the universal gerb, since every 3 class on Z can be represented by such a gerb, right? But so that's because PU is a classifying space for the circle. I mean, and a little bit of an argument. So I don't know what's happened here. So it doesn't work. Can you just kill it or something?
Does it do okay when it starts scanning?
Ah, this here? Yeah, okay. Okay, sorry. Thanks, Peter. So the holonomy line bundle. So I just want to say that, you know, the holonomy of just an ordinary line bundle with connection, it can be viewed as a circle-valued function on loop space. So now for a gerb, it's one higher. So a gerb with connection, the holonomy of it will be a line bundle on loop space. Okay, so it comes with connection and other things. So let me just say what a connection on the gerb is. So you remember gerb is line bundles on overlaps, and then you choose a connection on this line bundle, and it has to have some property. So of course, these line bundles are have satisfied this property, or on triple overlaps. So you need the connections which are locally of this form d plus a alpha beta to have the property that the curvature of this connection is b beta minus b alpha, right? So it's got the special sort of, so it's not an arbitrary connection on this this local line bundles, but it's got to have some relation with B's. So you have HBA. So the holonomy of this gerb is a line bundle over loop space, and so this line bundle has invariant local section sigma alpha, and these sigma alphas are related by sum of the data, which is e to the minus square root of minus 1, the transgression of a alpha beta. So a alpha beta was the one form which is part of the connective structure on the gerb, right? So of course, when you transgress it, it becomes a function. This is one form, but it becomes a function. So, and this is the transition function of the holonomy line bundle. And just to remind you what the transgression is, the transgression is a map from forms on U alpha I to forms of with one lower degree on loops on U alpha I. And it's defined to be, you take the evaluation map and you pull back under the evaluation map. So the evaluation map takes the circle across the loops on U alpha to U alpha and takes gamma, T gamma to gamma of T. You pull back under that and integrate along the circle, but the integration along the circle, you lose 1 degree. So this, so we have this line bundle on loop space, which is associated with the gerb with connection. But this line bundle actually comes also with a connection. So the connection is a nabla of L, and it's d minus square root of minus 1 transgression of B alpha. So B alpha, remember, was the local 2 forms. And this is a connection form. And the curvature is minus square root of minus 1 transgression of H. So it all fits in very neatly. And you get, so from a gerb with connection, you get a holonomy line bundle with connection. Okay, so, and also this line bundle is never flat if H is not 0. You know, if it's A, at least cohomologically, it's definitely not 0. And now we consider differential forms on loop space with values in this holonomy line bundle. So this is usually never studied. You know, nobody studies differential forms with values in a non-flat line bundle. But the reason why you can get a differential is because there's a tight sort of connection between the gerb and the line bundle. So here's a construction. So the thing to notice that so loop space, you have loop space here, it's gigantic, and then you have the constant loops sitting inside here. Z sits inside as constant loops. Right? And now, given any differential form on Z, when you view it as a differential form on constant loops, I will give you a way to extend it to all of loop space. Okay, so this is the construction. So first you define something which depends on an S parameter. S is in 0, 1. So you get a differential form starting from omega, you get omega hat of S, which is a differential form of the same degree on loop space. It's just defined in a tautological way. So you take vector fields x1 to xi, and these are vector fields on loop space, which is defined near the loop, right, the original loop. So, and you define it to be omega applied to x1 at the point gamma of S, and xi at the point gamma of S. So this is a point on the manifold. So this makes good sense. And it's easy to check that D and hat commute. Now, this looks good, but the problem is it depends on the S parameter. And what you do is just integrate it out. So you integrate with respect to S, omega hat of S, so call that bar, omega bar. And again, omega bar is an extension of omega to all of loop space. It's invariant under the rotation action, and the bar commutes with D. And an important formula is that the transgression of omega, right? You can transgress omega, and you can bar omega, and there's a close relation. So the transgression of omega is equal to, you just bar omega, that gives you a form of the same degree, and then you contract by the rotation vector field. And that's the relation between this extension and transgression. So now I'm in a position to define this cohomology on loop space, which localizes to twisted cohomology. So let H be the closed integral 3 form on Z, then you can extend it by the bar construction to a 3 form on loop space of Z. And since H is closed, then bar of H is also closed, because we saw that bar commutes with D. And define this differential. I'm going to show it's a differential, but define this operator. The connection, which we got from the gerb with connection, the connection on the holonomy line bundle, minus contraction by the rotation vector field, plus H bar. Looks like a sort of complicated thing, but we compute this, so I'll give this calculation because it's neat. So the square of this operator is 0 on the invariant forms with values in the holonomy line bundle. So what's the calculation? So you take U alpha, Berlinski open cover of Z, then H bar on loops on U alpha is D B alpha bar. So you can take the bar of B alpha. So this is defined on loops on U alpha. And now we can compute the square of this operator. So the connection is D minus contraction by the rotation vector field of B alpha bar. And then you have minus IK plus H bar squared. So you can rearrange this as D minus IK plus D minus IK B bar alpha. So because H bar is D of B alpha bar, which is also IK, so you have, so this factorizes, so this is dB alpha and IKB alpha is here, and this is here. So this is just like the written conjugation trick, but now instead of functions, you use even forms. So it's exponential of minus B alpha bar, D minus IK, exponential of B alpha bar squared. And when you square that, it's just minus the Lie derivative of the with respect to rotation vector field minus the Lie derivative of B alpha bar. But B alpha bar is invariant, so this is 0. And you get just the Lie derivative remaining. And of course, so this is the Lie derivative. And remember, we have some invariant sections. So we see that the Lie derivative is actually the Lie derivative on the line bundle. And so the square is equal to the Lie derivative on the line bundle. And therefore, it vanishes on the invariant line bundle valued forms. So the upshot is that this operator is a flat T-equivariant superconnection in the sense of Quillen. And this is a Z2 graded complex. We call the cohomology of this complex the exotic T-equivariant cohomology of loop space. Of course, now it's only Z2 graded, but you can fix the grading by putting a U over here and a U minus 1 over here. So then it's of degree 1. So you recover the Z grading, but then you have to put Z coefficients here. U over here also, power series in U. So the completed version of this is you put a U inverse, as I was saying, and then you put the U is of degree 2, so this reduces degree by 1, but raises it by U raises it by 2. This increases degree by 3, and U minus 1 decreases it by 2, so you get a degree 1 operator here. So the other thing to notice, so that this isn't that shocking, is that the holonomy bundle is canonically trivial when you restrict to the constant loops. So therefore, the restriction map, it turns out, is a well-defined map from this exotic equivariant cohomology to the twisted cohomology with U inverse. Well, just because of this comment, and this is actually an isomorphism. So this is the result that takes a major portion of the paper in 2015. So we suggested the following two proposals, that Ramon fields in string theory are exotic. So these are line bundle valued forms on loop space that are invariant, and the charges also lie in this space. Well, but it turns out that we won't really use this, but we'll use the fact that we have these line bundle valued differential forms on loop space. So that's probably, yeah. So I was going to talk a little bit about the twisted So, I mean, I just want to say that you get this, and so, so by this theorem, because the restriction, so you can lift the Tduality isomorphism to loop space, is what this theorem, this localization theorem gives you. So this is one result, but recently we were able to give a direct proof of it without the localization. So, so this is the end of the discussion on loop space. So the last part will be on how to fix the problem with momentum and winding. So are there any questions on the loop space part? Yeah. So all we wanted to find out is what's the cohomology on loop space that localizes the twisted cohomology, and the answer was very surprising. It was some line bundle value differential forms and some very unusual operator on it, so which is a differential. Not at this stage, no. That goes to double loop space, yeah, but not at this stage, yeah. It's the same degree shifting thing, because the localization, you get, so there's a degree shifting map here. So I would say this was the loop space version of 2A, maybe, and the loop space version of 2B. Okay? So I'm trying to make the configuration space much bigger. We didn't know why we wanted it, but now we know. So, after the fact. So maybe, is there any water here? Could you take some water? Okay, now, so ultimately I'm going to use this just on differential forms on spacetime, right? So, to make it natural, we go to loop space and argue. So Z was the principal circle bundle with flux form H, and let psi be the complex line bundle associated with the circle bundle, and then Z hat be the Tdual circle bundle with flux H hat, and the associated complex line bundle is psi hat. Okay, so now, I want to define an infinite number of embeddings of the manifold Z into loop space. So IN, so iota n at the point x in Z is just this loop. T goes to gamma x t, which is t to the n dot x. So here, this t is in the circle, and somehow this t is the circle of the circle bundle, right? So, and I claim it's an embedding. It doesn't look like an embedding, but it's an embedding to the loops on the fiber. The fiber is a circle, and the loop space of the fiber has infinitely many components. Each component is labeled by the degree. And so for degree, this maps it to degree n loops, and it's injective over there. So it's just saying that we are essentially embedding to the vertical loops. So the other thing is, if you pull back this holonomy line bundle on loop space, via this embedding. This is just psi hat, right? Ray tensor power n. Okay, so, and you can check that by calculating the Chern classes. So the Chern class of iota 1 pullback of L is just the transgression of H, and C1 of psi hat is just the integral of H. So they are equal. So loop space has the natural circle action by rotating loops, and Z has a circle action, which is total space of a circle bundle. And the tell difference we will call use S1 for the circle which consists of rotating loops. And then we have that the restriction map of this embedding maps say k bar, say even or odd forms on loop space with line bundle valued forms which are invariant, and it maps to even or odd forms on Z with values in psi hat bundle raised to the nth power, because the nth power comes from this embedding. And moreover, it intertwines the equivariantly flat superconnections on both these spaces. So that's the important thing. So we saw this superconnection on this space, and there's a natural superconnection here, such that this intertwines the two superconnections. So assembling these morphisms, so for each n in an integer, we get a morphism, which is a pullback under the embedding. So we take the direct sum of all these. So we get a map from all forms on loop space with values in the holonomy line bundle to these things which we call AKT, which is just the direct sum of these forms with values in tensor powers of the this dual line bundle, this T-dual line bundle. So what's the equivariant differential on this side? So I didn't say that explicitly. It turns out that it's this connection on psi hat, actually. Sorry, there's a hat missing. Tensor n minus this vector field, vertical vector field in the T-dual direction, but multiplied by n, because that's this n, and plus h hat. So, so this differential commutes with the equivariant differential, which we saw before on loop space with values in this line bundle. So on the subspace of weight minus n differential forms, so these are, so now, we look at differential forms on Z. So in the work with Peter and Jara, we looked at invariant differential forms. Now we take the higher weight spaces. So these are labeled by n. So we only looked at the n equals 0 weight space. But now, so if you take these weight spaces, so yeah. Yeah.
In this space, is it the same as differential form with these values on OM bundle on the base? On the last line, so I'm interpreting this omega as a form of the base.
No, yeah, but
The value be OM bundle.
yeah. Okay. Sorry, this is just a usual Lie derivative. Yeah. Yeah. Okay. Yeah, surely. So we just wanted to see what the correct transform was on these these higher weight spaces. So the correct transform is this tau n, which I'll define using this exotic. So on one side, these are just differential forms, but the other weight spaces, not just the invariant forms. And on the other side, we get these exotic forms, which are the pullback of forms from the loop space, line bundle valued forms of the loop space. So when n equals 0, we get the usual, the earlier work. So I'll define this tau n soon, so our main theorem shows that d plus h on this side, on just differential forms, goes to, under this map, which I haven't defined yet, goes to this differential. And you can, there is also a reverse map, which goes from this exotic forms to just the ordinary forms on the T-dual. And you can easily figure it out. And the point is that when you compose the two, you get minus the identity. So it's sort of saying that T-duality applied twice returns to minus the identity. So let me just tell you what the formula is, because I haven't yet told you what the formula is. So there are actually two theories. Sort of one side it's just usual forms, and the other side exotic forms. And the differential is a combination of these exotic differentials on one side, and on the other side it's just the twisted differential. So I'll eventually get to the formula, sorry. So now we are able to define momentum and winding in this larger configuration space. So the multiple of the circle winding is called, so you look at the number of times you go around the circle in the circle bundle, that's the winding. And the momentum is the tensor power of psi. So, and the point is that for to show that we show that one must have momentum on spacetime equals winding on the T-dual spacetime in order for the exotic differential to be equivariantly flat superconnection. So our slogan is momentum on spacetime gets exchanged with the winding on the T-dual spacetime, vice versa. So what's the formula? Let's just talk about it. So we introduce a twisted version of integration along the fiber. So we've used integration along the fiber before, but now we'll kind of define a twisted version. So let P be a principal circle bundle over M. Maybe I should have called it Z, sorry. Let theta be a connection one form on P, and L be the associated Hermitian line bundle on M. Let nabla L be the connection on L, corresponding to theta. And just note that smooth functions on P is a direct sum of smooth sections on L tensor N, right, over M. And you take the direct sum over all n. And so we can kind of, this is an intuition of why you can define a twisted integration fiber, which is maps differential forms on P to forms of degree 1 less on M with values in L tensor N. So when n is 0, it's the usual integration along the fiber. So let me explain this since this is new. So choose a good open cover of M, so U alpha, such that so the inverse image of U alpha under pi, so pi is this projection of the circle bundle, is just U alpha across the circle. And let f alpha be a local basis of L corresponding to the constant map u alpha goes to 1 inside the circle. So define twisted integration along the fiber. So this is the notation for it. There's an n to say that it's an L tensor n. So it has the property that if you restrict it to u alpha, it's the integral of pi inverse of u alpha over u alpha. So it's an integration along the circle. But you multiply this form omega alpha, this local form, omega restricted to u alpha is omega alpha, and you have exponential of 2 pi r n theta alpha, right? This itself is not invariant, but if you tensor by f alpha tensor n, then it is invariant. So this f alphas are defined here. Theta alpha is the vertical coordinates along this circle. And f alpha over f beta is this e to the 2 pi I theta beta minus theta alpha. It's a function on u alpha beta. So this construction is actually global. It's independent of all choices. And it's also independent of the good cover. So it really generalizes integration along the fiber and could be useful in many other situations. So this is the theorem. So let Y be a vector field on M, Y tilde with a lift to P, and H be a form on M. Then you have this, so the connection on L tensor N minus contraction by Y plus H of the integral, the twisted integral of omega. It's equal to this quantity, which is d plus n theta minus I y tilde, which is the lift of Y to P plus H. So the exotic Horry formula, they look exactly like the Horry formula, but instead of integration along the fiber, you use twisted integration along the fiber. So you take omega minus n, which is in this weight n or weight minus n space of z, and you apply tau n of omega minus n. This is by definition omega minus n, and this is the usual Horry or twisted Fourier-Mukai transform. And then you integrate, use twisted integration along the fiber, and you end up in this not on differential forms on z hat, but differential forms on z hat with values in psi 10 to the power n. So this is the formula that gives you the extension of the Horry formula to all weight spaces on one side, and you end up in exotic weight spaces, spaces on the other side. So exotic differential forms on the other side. So there's a long check. I won't go through it. I'm also very tired. So that's the point. I mean, it looks like the usual Horry formula, but you replace just integration along the fiber by this twisted integration along the fiber, and amazingly it all works. So the payoff for doing all this is that you can discuss the exchange of momentum and winding. And then there is a way to formulate this for K-theory also. So again, Kahler actually defined it so for invariant differential forms, invariant part of differential K-theory. And now it's possible to do it for all of differential K-theory. Then the question is, what about enhancing Tduality for torus bundles? And it's an interesting question. Project for maybe some students. And then someone asked me this question, and I asked myself the question. So can you do it in the supersymmetric setting? So that's it. Thank you for listening. So I don't have a thank you slide. Yeah.
So you think like the simplest possible example of Tduality of like S3 is 25 and S2 on the side with 1 unit. So on the S3 side, the I1 is trivial, so like there are no winding rates.
No, but the winding is only in the circle direction. So there are circles in the Hopf vibration, and it's winding on those sides. Sorry?
You can all deform them.
Yeah, I understand you can deform them globally, but
Yeah, I guess that question is like, why would you expect an integer winding?
so it's if you stick to just a circle, there is a winding there. So it's that winding as opposed to the global homotopy of the S3. Yeah, you restricted to fibers. Yeah. Yeah. Okay, thanks. I'll look at it. Yeah. Right. Yeah.
When you go for loops,
Mm-hmm.
and you've got winding modes with an answer,
Mm-hmm.
there's a way to go back to the space.
Yeah. There is by those embeddings.
So then I'm asking, is it possible to go back to the space but include part of the winding modes?
Mm-hmm.
Do you understand my question? Sometimes you have a natural problem.
Right. Right.
And then normally we associate with space-time.
Mm-hmm.
We don't talk about space. But what the work of Gregory Harvey and Paul was saying is that you actually don't have, you can't disentangle the winding mode of the space as a result of having this.
Yeah. Right. Yeah.
How do you see the order of space?
Well, clearly these, you see there's no issue if there's a product manifold, right? Right. And this is one way to incorporate, to give this to extend the Tduality isomorphism, right? And the point was to discuss winding and momentum. So our definition of winding is the number of times the vector field goes around the circle, only the circle direction, not globally. So I think there's an issue between global winding and fiber-wise winding. So I think in the product manifold you look at just the circle winding. You just wind along the circle, right? You don't care about the topology of the other part.
Doesn't this come down to a question about the loop space?
Yeah.
Of Z, if Z is S3,
Yeah.
right? You don't have disconnected components of the loop space.
No, but we have fiber-wise, the fiber loop space, the vertical loop space does have disconnected components. So loops on the circle is.
No, I understand loops on the
So this is the way we embed it.
But I mean, at some point we were talking actually about the loop space of Z.
Yes.
Right? And
no, that doesn't necessarily.
That actually has components.
Yeah, I mean that depends on the fundamental group of Z. But the way we embedded it was vertically. because this is not just an arbitrary space, but there's a circle bundle. So you can embed it actually vertically. So there's an embedding into the vertical loop space, which is a subset of the loop space of the whole space. So it's a kind of very special embedding. So which mixes the rotation of the circle, of the loops, and the circle action of the circle bundle. So we always get Z components. So yeah, so you also.
So you basically, if you look at your construction, you are telling that you can take an arbitrary differential form, expand the mode, go to another object.
Yeah, which is an exotic object, yeah.
What about multilateral groups?
We did the current algebraic version also, except I can't remember what else. So, do you remember, Faye? So the current version of this. So so we discussed that also, the current algebraic version.
So you know how non-invariant fields will be transformed?
Apparently so, yeah. So they will be transformed to some exotic sort of things. Well, I don't know. I have to look at the paper and tell you, yeah. So I think we do have that, yeah.
Let me comment on the last question. So we looked into this with Isham recently, with supersymmetric Tduality. So there's this interesting effect that when you go to superspace, the R forms the Gaussian constraint of this fixed bifermionic piece, which is just fixed, not given. And one can check that it satisfies this super form, the axioms of the
Yeah. Okay, cool.
You can read off the axioms.
Right.
So it suggests, I mean, we just looked at that bifermionic piece.
Yeah.
It works.
Right, good. Yeah, I know some people did work on it way back. And then, so I'm saying, is there an exotic version for the fermionic stuff, also supersymmetric stuff? So I don't know. So whether you have to use just invariant ones, or can you take all weight spaces? Yeah. So it opens up some interesting areas, I think.
Is there a measurable way to reduce this or
Well, there is a question, but I was trying to leave it for for Jacqueline. Yeah. Yes, there is something that you can formulate for spherical Tduality also. I don't want to talk about it. Yeah, sorry.
What is the desired
No, it's a complicated thing, because if you want classical Tduality on both sides, you need to assume something on H. H restricted to the fiber is cohomologically trivial, and then various other things, some spectral sequence condition on H. Then you get classical Tduality. But then it's also invariant forms on both sides. So the point is whether it just extends to the non-invariant forms, just like in the circle bundle case. But of course, in the torus bundle, there are restrictions on H, which are known. They're completely known for classical Tduality. So you get exchange of momentum and winding in this case also, the torus compactification case. Okay, thank you. Thanks so much.